12.6, circular and periodic functions, continuing on with our trigonometry section. Good times with SOHCAHTOA. Little review. What information allows you to solve a law of sines cosine? Remember, law of sines, we are looking for either SAS or SSS. So it's not that one. Two angles on any side, that would be law of sines. And two sides in the angle opposite one of those sides, that would be law of sines. I believe it's two sides and the included angle. Answer is A. Okay, the unit circle is going to be a circle with a radius of 1 unit. So the beauty here is that we have an r equal to 1. So if you remember back to sine was equal to y over r and cosine was equal to x over r, this is where we really get ahead now, in that if you're talking about a circle with a radius of 1, the sine will be equal to the y coordinate and the cosine is equal to the x coordinate. Please make note that this is only the case when r equals 1 and we're talking about the unit circle. They need to tell you that. So I think there's a few slides here that kind of say the same thing. So now we go on to, instead of on a coordinate plane, and what we did at some point is we have an x and a y and an r, and now instead of just having to worry about using this angle and doing opposite over hypotenuse and adjacent over hypotenuse, since this is always going to be 1, it's x over 1 for cosine and y over 1 for sine, which means the x coordinate is the value of the cosine and the y coordinate is the value of the sine. The number one place where this is going to be useful to you is the quadrantals of 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Because now if you know you're talking about a unit circle, it's very quickly to say the cosine of 0 degrees is 1 because it's the x coordinate, and the y coordinate gives you the sine. So we're still going to do all of the same types of things. So if they gave you a theta of 120, we're still going over here and we're doing a 60-degree reference angle, except now I'm going to be able to, I could have a triangle, but now we're going to do things a little bit differently. So we're still going to do a lot of the same stuff, but it'll work itself out. This says the same thing. This is for the circular functions. Okay, so very simple example. They're telling you it's a unit circle. That's really important. And this is the x coordinate, and the x coordinate is the cosine. Since that's x and that's y, then I have a cosine of square root 7 over 4 and a sine of 3/4. It's that easy. And if you think about putting it on here, the x coordinate, square root 7 over 4, 3/4, and this is the beauty of the unit circle. Here's my theta, adjacent over hypotenuse, that's the cosine, opposite over hypotenuse, that's the sine. So this goes pretty quickly in that find the sine and the cosine. I mean, we can say the cosine is the x coordinate, the sine is the y coordinate. Again, they have to tell you it's the unit circle, otherwise we can't necessarily say this. Next thing, period. Let's actually take a look at, I'm going to take a look at a quick little website here. Let's go to, let me see if I can find it. Here we go. Okay, we took a look at this at one point, this interactive unit circle. So remember, my sine is my, let me make it bigger for you. My sine is my green line. So now we're saying at 0 degrees we're 0. at 90 degrees, and I'm on a unit circle here. So at 90 degrees, I'm 1 because the y-coordinate is 1. At 180 degrees, I'm 0 because the y-coordinate is 0. And we can see this. And the graph over here on this guy, you know, we go up to 1, we come down, and we're at 180, and we're at 0, and then we're at 270. We're down there, we're at -1, and then we come back up. So remember, the period is going to be how long does it take me to go around a circle? Well, it takes me 360 degrees to go around a circle. There I am. And when I graph this, what I'm doing is I have the degrees on the x-axis and I have my ratio on the y-axis. How long does it take me to get back to where I started? It takes me 360 degrees. Cosine, if you look at the blue one, let's look at the blue one now. The blue one tells me my cosine starts at 1, and I go up at 90, I'm 0, x-coordinate is 0, 180, I'm -1, and 270, I am 0, and then I come back and I'm 1. So I'm going one rotation, I'm going through the whole thing, one cycle. That means the period for sine and cosine is 360 degrees. So we come back over here and we say, what is the period of this function? Well, this is a funky function that wouldn't necessarily have a nice graph for us, but if I'm starting here and I'm going up, so I go up, over, down, up, over, all the way down, over, up, over, down, and up. So there I am, back at the origin, heading up. That means my period for this one is pi over 3. So then I do it again, and there I went through it again. I'm at 2 pi over 3. Go through it again. I'm at 3 pi over 3, or 1 pi. Period. I'm starting, where am I starting? I'm starting at -1, and I'm heading up. I go up, I go down, and now I'm back to -1, heading up. My period is pi. So that's why when we're talking about the period of sine and cosine, we're going to be talking about the period is 360 degrees in degrees, or 2 pi in radians. Let's see here. They want us to, the pedals on a bike go round and round. So we are graphing the, let's see, what are we graphing? We're graphing time. This is time on this axis. X is time. Y is height. Height versus time. So they've graphed this, identify the period of the function. Well, if it takes 2 seconds to come back to the top, then the period is 2 seconds. Right? So at time 0, if I was to graph this, let's graph from 0 to 2 seconds. At time 0, I am 18 inches tall. At time 0, I'm 18. At time 0.5, I am 11 inches tall. At time 0.5, I am 11. At time 1, I'm 4 inches tall. And then I start going back up. At time 1.5, I'm 11 inches tall. And then at time 2, I'm back to where I started. And you can see we'll have this nice sine curve idea, and then I would come back around. Whoops, got a little squiggly in there. Sorry about that. So we can see that if we start here and end here, that's 2 seconds that we can do, we can get through, and we can do our 2 seconds for our period. Unit circle, we used to have to memorize this stuff. We no longer do that. They all run off of the following. This goes back to what we did in 12.3. You need to know this. 1, 2, root 3. You need to know this. 45, 45, 90 is 1, 1, root 2. And you need to know when the sine, the cosine, and tangent, whoa, STC, what are you doing? Let's change colors. This is an S, this is a T, chilling in the STC. Tangent is positive in quadrant 3, cosine is positive in quadrant 4. So this is the same method. You're going to do the same method. You're going to find reference angles, and you're going to use the STC, and you're going to use the 45, 45, 90, and the 30, 60, 90s. You could take and say every unit circle, I'm going to divide all of these things by 2. Divide by 2, divide by 2, divide by 2, and do x coordinate, y coordinate. But we have found that just using the reference triangles and using the STC is actually a better way to do it. So when we take a look at the exact value of 690, the first thing I'm going to do is I'm going to figure out where I am. And if I am 360 and then around to 690, I will be 30 degrees short of quadrant of 720, which would be 2 times around. So I'm going to use a 30-degree reference angle. The reference angle is always formed. I know I'm cosine in quadrant 4 will be positive based on this. And then I just get my reference triangle for a 30, 60, 90, and I should know that the cosine of a 30-degree angle, and this is going to be positive. You don't have to write the plus. I'm just doing it to show you where it came from. And cosine of 30 will be square root 3 over 2. And that comes straight off of 1, 2, square root 3. And there's my cosine, square root 3 over 2, and I know it's positive because it's quadrant 4. So you can use the STC and the reference triangles to do all of these exact values. Very similar to what we've done in the past. Oh no! We've got to do negative 3 pi over 4. If you're not sure what that is, then you should convert that into degrees. If you convert this, it's 135. So if I went negative 135, it leaves me 45 short of my 180, which means I'm going to have sine in quadrant 3. So the sine of negative 3 pi over 4. It's going to be a quadrant 3 sine, so it has to be negative. And then I'm going to do 45, 45, 90, which is 1 over the square root of 2, or square root of 2 over 2. You're going to get that right off of the reference triangle for 1, 1 root 2. And then I know that when I do 1 over the square root of 2, I got to change that to square root of 2 over 2. 660 cosine. Again, I think we're going to be in quadrant number 4, and I think we're going to be a 60-degree reference angle. Quadrant 4 cosine, positive. Can't be this one. Can't be this one. Cosine of a 60. 30, 60, 90, 1, 2, square root 3, cosine of 60, 1/2. Boom, it's B. So you're going to go off of STC for the sine, and then you're going to use the reference triangle. Always make the reference triangle with your x-axis. Things will be okay. Negative 7 pi over 4. Again, 8 pi over 4 would be 2 pi. So I'm going to come all the way around, and I'm going to be a pi over 4 short. If I'm 1 pi over 4 short, I'm 45 short. If I'm in quadrant 1 with a sine, can't be negative, and I think we know that 45 is going to be square root 2 over 2. Good stuff, huh? Good stuff. Exact values. Now you're going to add things together. So you're going to find the sine of 45. So again, you're going to use STC. You're going to use 45, 45, 90 of 1, 1 square root 2. You're going to use 30, 60, 90 of 1, 2 square root 3. Sine of 45, got to be positive, square root 2 over 2. Plus cosine of 30, here's 30, cosine square root 3 over 2. Got to be positive. And then I would just put them together as a single term. And that's an exact value. No decimal equivalents here. We must have simplified square roots. Let's actually do sine 45 times cosine of 30. Just, you're going to get some more problems like this. This would be square root 2 over 2. This would be square root 3 over 2. When I multiply them together, I get square root 6 over 4, and I'm done. That would be an exact value. So basically, we're doing a lot of what we did in 12.3, which is the STC and the reference triangles. Good talk.